Welcome to the lesson on singly linked lists. So far, our data has always lived in an array, where the items sit side by side in memory. In this lesson we meet a new idea. Each item can sit anywhere in memory, and a pointer tells us where the next item is. This one change makes many edits much cheaper, and we will see exactly why. Let's start with a simple question. Why do we need linked lists at all? To answer it, we look at one small job that an array does very badly. This is what you will be able to do after this chapter. First, you can explain a layout that is not contiguous. That means the nodes may sit anywhere on the heap, joined only by the next pointer. Second, you can read one node byte by byte. You lay out its two fields, data and next, in memory with padding and a real address. Third, you can reason about the core operations. Those are traverse, search, insert at the head, at the end, or after a node, and delete. And you can say what each one costs. Fourth, you can move the pointers in the right order. The rule is simple. Link before you unlink, and relink before you free. Fifth, you can write and free a list in C. You build each node with malloc, and you destroy the list with one matching free per node. One idea drives the whole chapter. Order comes from the next pointers, not from where the nodes sit in memory. This one choice makes structural edits cheap. It also costs us constant time indexing. This is the path we take through singly linked lists, one step at a time. First, what a linked list is. Nodes joined by next pointers, not by position. Then a node in memory. We look at one 16-byte node and why order lives in the pointers. Next, traversal and search. We walk from head to null and we find a node by its value. Then insertion. We add a node at the head at the end, and after a node we hold. After that, deletion. We relink past the node we want to remove, then we free it. Then complexity and pitfalls. We see what each operation costs, and the classic bugs in C. And last, arrays versus linked lists. We see where each one wins. Picture a music app. It holds its playlist in a fixed array, like the ones from Chapter 2. The songs sit back to back in memory. Here you see 5 songs at index 0 through 4 and one empty slot at the end. Now you want a brand new song to become track number 1. That is the new front of the list at index 0. But look, index 0 is already taken. The song 17 lives there at address hex 1000. The only free space is slot 5, way at the end, at address hex 1014. It is empty, but it is the wrong place. We need room at the front, not at the back. So here is the problem. To make index 0 free, every song already in the array has to move first. The next slide shows exactly what that costs. Let's watch the front insert happen, one frame at a time. We want to put the value 30 at the front. The copies run from the back, so nothing gets overwritten. Amber marks the cell being moved. Green marks its new home. Frame 1. The array is full, and index 0 holds the song 17. Every one of the 5 songs must shift right by one slot before index 0 is free. Frame 2. We copy from the back to the front. Slot 5, then 4, then 3, then 2, then 1. All 5 values move one slot to the right. Now index 0 is an empty hole. Frame 3. We write 30 into the hole at index 0. 5 elements move just to insert one. For 10,000 songs, that is 10,000 moves. This is big O of N work. So what do we want instead? We want to insert at the front without moving any existing song. In an array this is impossible because the songs sit next to each other. The fix is to stop storing them that way. We give each song a field that holds the address of the next song. Now the order comes from those addresses, not from position. A new first song just points at the old first song and nothing else moves. That pointer link chain is a linked list. This is the picture. Head points to the new song 30. Song 30's next field points to 17. 17 points to 42, and 42 points to null, the end of the chain. We added one new node and redirected one pointer. The old songs never moved. This is big O of 1 work. Now let's see what we trade for these pointers. Look at the first row. Insert at the front of 10,000 items. In a naive array that is big O of n because we shift all 10,000. In a linked list it is big O of 1 because we link head. Second row. Insert right after a node you hold. The array must shift the whole tail, which is big O of n. The linked list only does 2 pointer writes, which is big O of 1. Third row. Grow past the capacity. The array must realloc and copy everything. The linked list just calls malloc for one new node. Fourth row is the other side of the trade. Reach the ith item. The array does it in big O of 1 with simple address math. The linked list must walk the chain, which is big O of n, so we gain cheap structural edits by giving up constant time indexing. The rest of the chapter makes that trade concrete, address by address.